Let's do a straightforward example with the Fourier transform, and in doing so we will learn about its properties a little bit, and we'll also learn about a very important concept known as the Sinc function. So I'm going to go ahead and create a set of time axes, and we're going to create a nice simple square pulse that I'm going to center around the y-axis. And we'll call that x of t. And just to keep things interesting, let's say it goes from -5 to 5 with a height of 1. And I want to find the frequency content of this signal. So I'm going to apply my Fourier transform integral, which tells me that a of omega equals the integral over all time. So again, remember that I'm integrating over all time, but there's really nothing to integrate outside of the region from t equals -5 to 5, because outside of that it's 0, so there's nothing to integrate. So my integral over all time is really just going to simplify to -5 to 5, and it's x of t, which is 1, e to the minus j omega t dt. So I work the calculus, and that gives me 1 over minus j omega e to the minus j omega 5 minus e to the minus j omega minus 5. And I'm going to be slick and notice that what we have here in the brackets is really minus 2j sine 5 omega. Don't forget that in general, sine of theta equals e to the j theta minus e to the minus j theta over 2j. Okay, so that's an identity. By turning that identity around, I got this minus 2j sine 5 omega term. And I'm going to let stuff cancel out, and I'm going to write that as sine of 5 omega over, and it should just be that times a 2, so it should be 2 times sine 5 j omega over omega. But what I'm going to do is, so technically this is the right answer, but what I'm going to do in order to put this in a more common form is I'm going to multiply numerator and denominator by 5, and I'm going to rewrite this in what's a little bit more of a standard form, which is 10 sine 5 omega over 5 omega. Now, this sine omega over omega business, this is what's known as the Sinc function. And we will see it pretty much everywhere we look for the rest of time as we study signals. So let's see what that means. Let's go ahead and plot it. So let's just work on the magnitude plot for now. So this is j omega. This is the magnitude of a of omega. And just for the sake of argument for today, usually we omit the negative frequencies, but for today I'm going to plot them. So what I've got is a sine function that's divided by a constant. So what we can sort of think about is that we're going to have a sine function whose amplitude gets smaller as omega gets bigger, which almost completely describes this thing, except for the very lowest of frequencies at omega equals 0. You wind up with a sine of 0 over 0 term, which necessitates you do L'Hopital's rule, and I'll spare you the drama of going through that. When we finish it, and we plot it, we're going to get something that looks like this. And again, this is just the magnitude. Okay, and then we know that the magnitude is always going to be an even function. So we know whatever we get on the right-hand side, we're going to get something roughly equivalent on the left-hand side. Now, in this particular case, this is 10. This is going to be, let's stick with green, this is going to be a frequency of pi over 5. Okay, and the reason I know that is that my 0 crossings have to occur when the numerator of my function is 0. So I know that sine of 5 omega equals 0 is where I get my first 0 crossing. And I know that my sine function equals 0 when the argument of the sine function is 180 degrees, or pi. So in other words, when 5 omega equals pi, then sine of that should equal 0. So in other words, my zero crossing should be omega equals pi over 5. And that's where I get that number from. Okay? And then the rest are evenly spaced. This will be 2 pi over 5, 3 pi over 5, and so on, 4 pi over 5. Okay? So again, this is called the sinc function, and we're going to be seeing a lot of it. So two more things you should notice. The first thing is that the height of this function is, I found that it was 10, and it's no surprise that that 10 matches that 10, which is why I drew it in the first place. If I had left my function in this form, it wouldn't have been quite as obvious where the 10 came from. Alright, so we have that. And then the other thing that's worth noting, that's really interesting, is that usually when we take the Fourier transform, the result of our transform is complex. Okay, up until now, pretty much every a that we've looked at has contained complex numbers. But if you look at the particular value of a that we get here, which is 10 sine 5 omega over 5 omega, that's not a complex function. Okay, this is purely real. And that's because this is a special case. Okay, the particular function x of t that we're working with is a special case, and what's special about it is that it is an even function. And it turns out that whenever your x of t is even, you always wind up with a purely real Fourier transform. Okay, so this is a new property that we're learning. So when x of t is even, what you wind up with is a Fourier transform, a of omega, that is purely real. Okay? We'll look at some more properties down the line, but for the purpose of this video, really all I wanted to do was to introduce the concept of the sinc function, which, like I said, is going to be one of the most useful things that we look at in all of signals.